Let me quickly pull up the chat. Pop out chat. Where do I put it? Space 4. Cool. Number theory today. Hopefully there's some regulars. Oh, I'm probably gonna get copyright struck if I keep playing this. Bro needs help from his regulars. Yeah, I do. Can't do this without my regulars. Pajama Man, you're a regular. I recognize you. It would be cool to work on some programming too at some point. Maybe I'll do that this weekend. I haven't worked on our programming project in a while. It's making me kind of antsy. It'd be cool to pair program with people from chat too. Or just from my Discord server, I suppose. Just work on something. Just make the capitalist wheels turn on something. Okay. What? Okay, so I've done this one, I've done that one, I've done that one. That one is from last time. Johnny gave me the argument there. That's cool. Would be cool to do some lean streaming at some point too, but so much damn homework. Okay. There we go, there we go. That's done. For n greater than 3, show that they can't all be prime. Okay, we have 2 more, I guess. Well, 3 more. So 12. Pn to note the nth prime number, prove that the n plus 3 is less, the squared n plus 3 is less than the previous 3 primes multiplied together. Now that's an interesting one, actually. That is an interesting one. Could this be an induction question? Because, let's see, would it be an induction question? If you assume n and then show n plus 1, would that work? Would the algebra work out that way? I guess you could add, it really does seem like induction. Because you could add what to both sides to make that true. Unhelpful in your experience? Yeah. I Is that just because they're like the gap is pretty unpredictable at a certain stage? Um, Hope you're well too, Maglev. I have a question. I know math is intuitive like physics, so how could you study physics and look at problems, especially like conceptual questions? Like, how would you look at the questions to solve? I'm not sure what you're asking exactly. So, how would you study physics and look at problems, especially like conceptual questions? The nth prime doesn't really tell you about the n plus 1th. Worth a try. Yeah, I just think so. Like, looking at this, I was thinking, like, is the algebra going to work out in some way? Because, yeah, it's hard to say that the algebra would work out. P n plus 4 squared. Pn plus 4 squared is less than Pn plus 1, Pn plus 2, Pn plus 3. That Pn plus 3 would be is a little bit interesting. The algebra, though, it's not immediately obvious. Yeah. Well, yeah, how do we get the Pn plus 4? Add it, so, well, yeah, I'm not exactly sure. If I have a pencil and paper, I could work this out. I wonder if I can get my my other screen to show up. Can I add another video device? Add video capture device. macOS screen capture. No, where is this? Media source scene. Oh, video capture device. It's all the way at the bottom. Okay. Alright, make sure my camera isn't like pointed out my window. Alright. Sweet. Thanks, I appreciate that, Aziz. Have you ever gone into reverse engineering? You mean like reverse engineering binaries? Okay, I'm gonna have to set this up. And usually the way I do that is I take these ski poles and I put them across. And then once I've got that, which is kind of stable, I guess. What's up, Johnny? Yeah, you should really be getting paid. Once I do that, I put my phone like that. And then let me put myself a layer above the other video capture devices. How do I do that? There we go. Now I can zoom in on this. I guess I can rotate it. How do I rotate? There we go. There we go. Using no AI, very vintage. Yeah, I appreciate that. It's kind of scary times we live in if like AI keeps improving. Like, what's even the point of doing this? But just try not to think about it too much. It's like, I don't know, it's like Pascal's wager a little bit. Like, yeah, what if thought labor gets eradicated? I mean, stuff sucks, but like, it's not like it's super physically torturous for me to get good at math or programming. And then, yeah, so, no, I haven't reverse engineered binaries. I know a few people who do, though. It's really cool. It would be something to look into. Yeah, number theory today. Okay, we're doing... This drawing is annoying, rotating around. So the question... Oh, God. I need like a second scene where I can have my screen and I can switch between them. Oh, this one is called me plus screen. Nope, that's my OBS instance. Okay, I need a new ad. macOS screen capture. There we go. Oh, but now I'm like hidden. There we go. The question in question is proving that what's your exciting news? The question in question is proving this holds true for all primes, and I was thinking that this might be an induction question, like the induction algebra. I was going to try to work that out. And those are just like the nth primes. But it's a little weird because we're dealing with like indexing of primes, and I don't know if that'll directly work out. There might be like some kind of theorem or something I'm missing. Yeah, like the algebra seems like it might be possible, getting from that as an assumption to like n plus 1 on that. I guess I'll make the problem larger. And move myself. No, that's not the right problem. It's this one, number 12. Yeah. I want to quickly check what, I'm supposed to technically like read the textbook or some shit, but do I have an instance of it open? I sure do. This is 3.3, I guess. What does 3.3 cover? That'll probably give a big hint. It's the Goldbach conjecture. Oh, is my screen just really off center or what's going on? There we go. 4:3 monitor is really annoying. Let's see. Product of two or more integers, no. There are an infinite number of primes of the term 4n plus 3. Consider a prime number q is less than n. Theorem. If all n is greater than 2, then p plus d, p plus 2d, p plus n minus 1d are prime numbers, and the common difference d is divisible by every prime. That's somewhat related, but no. I don't see anything in here that's jumping out to me immediately. Yeah, I can go back to the question. It's question 12. Yeah. Bertrand's postulate. We have that the n plus third prime is less than 2 times the n plus second prime. Is this the same real analysis book? No, this is number theory. Bertram's postulate. I don't see that discussed in this section. Well, actually, I think it is discussed in this section. Bertram's postulate and his odd because it's strong. Goldbach's not an obvious or easy thing. Pretty sure you're not allowed to use it. Yeah, I don't think we did not cover it in lecture. Wait, I'm curious about what it is, though. Bertrand. Any integer there at least exists one prime. The less restrictive is for every n greater than 1. Really? That's crazy. Verified his statement. Bertrand himself verified the statement for all integers up to 3 million. He did that by hand? Is it hard to prove? Implies that the number of primes x denoted to pi x is roughly x log x. So if we replace x with 2x, then we see the number of primes up to 2x asymptotically twice the number of primes up to x. Therefore, the number of primes between n and 2n is roughly n over log n, where n is large. Yeah, we have not covered this. Oh, Sylvester's theorem. Erdős theorems. Yeah, nowadays everyone's weak compared to that. I mean, I guess, like, if there was nothing else to do back in the day, you would probably get kind of obsessive about it. Nowadays, people are like, oh, I'm sick, I can't do my homework. If you have barely anything to do, you are overstimulated and probably more likely to come up with that. Yeah, it's really unfortunate, honestly, that wow, my stream setup is messed up. It's unfortunate that we can't, like, easily go back to that. Like, you could go to, like, a monastery and just work on math all the time, but it's like, once you've tasted modern life, I feel like it kind of ruins you a little bit. At least it does me. Alright, so could this be proved by induction? It's worth a shot, I guess. Yeah, that was specifically meant for you. So, just the inductive step of this. P, that looks like an R, n plus 3 squared is less than Pn plus 1, Pn plus 2. If we're given that, could we get, well, getting the Pn plus 4 squared is not the easiest thing. Well, we could start with it. It would be equal to Pn plus 4 squared. What would it be less than? It would be less than, like, itself times a bunch of other stuff. No, I never cover probability. I might eventually. Well, Pn plus 4 Pn plus 4 is going to be less than Pn plus 3. That doesn't really, well, no, it would be greater. Yeah, this is tough. This is very tough. I'm not sure at all. When it's tough, you can just give up. I wish life worked like that. Okay, so the book does have a hint, and the hint is this. P of n plus 3, p squared of n plus 3 is less than 4 times p squared n plus 2, which is less than 8 times p n plus 1 p n plus 2. So they give that hint. That kind of implies, like, aren't they using Bertrand's postulate there in a way? Because that 4 right there implies that they've done the double trick twice. Because it's, well, they did it once, but then it's squared. And is less than 8 pn plus 1 pn plus 2. Yeah, that's just so I guess we are allowed to use that. Bertrand squared. Yeah, the hint is Bertrand's. Okay. Okay. And that's less than... all right. That makes things easier. Okay, so... we've got this is less than 4p plus n, or p 4p n plus 3 squared. And we can substitute in that weird thing to do in a first number theory class. This class isn't taught by a number theorist, it's taught by a combinatorist who just didn't want to teach it. Yeah, unfortunate. You don't need induction now, though. You don't need induction. You can just transform this algebraically. N plus 3 is less than 4 times its successor, which is less than 8 times that successor, problems involving size of primes are generally hard to do without an overpowered theorem. Okay, that's good to know. So let's go back to here. All right. This is called elementary number theory. It's taught by this guy who doesn't want to teach it at all. So he sends in his like PhD student to teach it most of the time, and then or he just talks about Erdős and like the history of mathematicians. Okay. So, I mean, they basically, the idea is that every prime is less than 2 times its, or greater than 2 times its successor. So Pn greater than 2 times. Or no, it's less than 2 times its successor. Because it's bounded. Hey, how's it going? Let me do some OSINT. On what, the class? Okay. So well, we know that P of n oh my god. We know that that is less than that squared. It's less than 4, just using their hint, times the successor squared, which is less than 8 times that bad boy times, so we're taking one lower. Successor or predecessor? Famous proof by Erdős. Okay, so then how do we get from this to that? We've got an 8. I mean, we just have to multiply by another. Okay, I mean, this seems fairly easy. So, oh my god, that's fucked up. That exponent. Okay, I think I know the algebra to do this. Why is this so wrong? Oh, there we go. That should be a plus. There we go. what does the assumption n being at least 3 tell you? Well, we can multiply through because it's positive. We could just multiply through by Pn, which would give us 4 Pn times P n plus 2 squared is less than 8 Pn plus 1 Pn plus 2, and then we're almost to where we need to be. Like this multi-line. And align it. Okay. So, I mean, we can then safely delete this down to a 2. Actually, you know what we can do? We can amp this up. So if we well, we can get rid of this P of n for free. If we make that Pn plus 3, then it's going to be less. So that's chill to do. Just how do we get rid of this 8 completely? So that'll go down to a 2, which is almost there. Yeah, Spencer Bachman, yeah. Good OSINT. What do you mean persona situation? Oh, the entire question. Here. Number 12. Good OSINT on that. I mean, I like him. I think he just doesn't really want to be teaching the class. So we got that. We got that. Now we just got this extra 2. How could we take the 2 away? I think, well, so in this little maneuver, we introduce a factor of 4. We just have to take away that factor of 2. I mean, this seems pretty easy. I'm just missing something obvious in the transformation. So from this stage to this stage, we're multiplying by 4. Wait a minute. This isn't okay. This isn't entirely clear. So this is fine. I think I was just sprinting too hard to get the left-hand side by eliminating that, and we need to do something to eliminate this 8. And just to confirm that that's positive. So if we multiply through by 3, yeah, how does that... That 8 is damn troublesome. I think you can just use that 8 is less than Pn. If n is at least 4 in the inequality that the hint gives. Eight is less than Pn. Eight is less than Pn. Oh. Eight is less than Pn. Oh, I see what you were saying, Pepe, about plugging things in, yeah. We don't even have to. Yeah, do anything that fancy, really. V0 dp. Okay. Yeah, that's clever. I see what you're saying. And then Pn equals 3 is less than this. I'm getting rid of this extra pn. We don't have to multiply through by... Oh, well, we do. Okay, we do. We have an extra pn on this side. And we can say this, we have that inequality, and then we can just say this, because obviously. Check the n equals 3 case by hand. It's the third prime. 7. 49 less than less than 2, 5. Wait, no. 2, 5, 7. N plus 3 is 6. Oh, yeah. Yeah, what am I saying? The 6th prime is less than the 3rd, the 4th, and the 5th. Why do you have to check this? Because we assumed, oh, the 4th. What's the 6th prime? 2, 3, 4, 5, 6, 13. Oh my god. Vim is so annoying sometimes. Maybe I should just use VS Code. P6 squared less than wait, 4th prime is 7. I to k y you consider 4 pn times pn plus 2 squared. This is number theory, not analysis. What do you mean, oops, year? You have to check 3 and 4. Don't we not? Because we did greater than or equal to. Isn't that fine? That checks 4. P3, P4, P5. So the primes are 1, 2, 3, 5, 7, 11. That's the 6th. (11 squared) less than 3 times 5 times 7. Same types document is still here. I used it on the other problem, actually. Here. Argument fails for n equals 3 and n equals 4. No, 7 is less than 8. Oh, P4. Oh, wait, 1 is not a prime. What am I doing? That's all fucked up. So the 6th prime is actually 13. 13 squared. You have P3 less than 8, P1 times P2. Less than Pn. So argument fails for n equals 3 and n equals 4. Yeah, that substitution. P greater than 4. Yes, well, since 8, P greater than 4. Verify n equals 3 and n equals 4. But I want to quickly see what Johnny's saying. You have P n plus 3 squared is less than 8. Pn plus 1 times Pn plus 2 is less than Pn times Pn plus 1 times Pn plus 2. Second inequality holds if n is at least 5. So for all cases except for n equals 3, 4, we're already done. And we only need to check the inequality we want. N3 squared is less than 8. Pn plus 1. Yeah. Yeah. that's annoying. We have to. Just for the sake of learning. Is there a way to do this without having to verify those two cases? I don't want to have to do like a little bit of arithmetic. That'd be really annoying. Ever considered using lean? And honestly, yeah, I'm just not sure about the difficulty level of using lean. It's pretty hard, isn't it? You don't need those lines like 4 pn n plus 2 stuff. Like right here. You have that you have that is less than 8. Is less than 8. Oh yeah. I'm technically like, this is just like an intermediary step to like help to help compute or just to help us see that that's true, I guess. So yeah, it's not at all necessary. You're right. Yeah, we just have that off the bat. I mean, yeah, this problem is really dumb and boring. Like that. It's literally just recognizing that 8, like, you can substitute in a prime, and then that's ridiculous. Or is that used for the intermediary step? But yeah. No, we don't need this at all. Okay, yeah, Bertram's postulate makes this very easy. Okay, and then this 13 squared is less than 5 times 7 times 11 times 11 which is just 169 77 times 5 55 times 7 is less than 55 times. I'm not. That's easily true. Okay, and the next case is what, 17? I'll delete this in a sec. 17, that's a 7, that's an 11, that's a 13, 77 times 13. I mean, yeah, this is obviously true. What's 17 squared? 10 times 7 times 7. 100. What's 100 plus 2 times 70? So 240 plus 49 is 289. what kind of black magic is happening. I'm 12. I'm in middle school. Talk to algebraic geometrists in my free time. So you're basically cooked. No way you're getting a job. Or it was intermediary step, but yes, for a dumb problem. Also, I'm afraid there is no avoiding the check by hand. Just think of the mathematics of old looking down on you, avoiding doing too small calculations. Well, Bertrand went on to do 3 million. No, can't do 2. No. What's 289 is less than 77. 770 is less than 770, which is which is less than 7 times 11 times 13. Can you imagine what Bertrand's like workflow was like when he was like verifying that? Like you wake up and you're like, all right, today I'm gonna verify integers between 2 million and 2,500,000. All right, here's my charts. I'm just writing this down. You can probably speed it up quite a lot for certain things, I'd guess. Because you could have like the sieve of Eratosthenes, so you'd have all your primes. And maybe it would be pretty quick, actually. Maybe you could line this all up. You have the sieve of Eratosthenes, you just have like a big chart of primes, and then you don't have a computer, but maybe there's some like geometric way to do this. Some pattern that would help in the proof. Yeah. Verification just comes down to having a list of primes. And they had Sieve of Eratosthenes, and they had like Euclid's stuff from before. Like there's a pretty efficient way to calculate what the primes are. Euler factoring 2 to the 32 plus 1. That must have been the method. Yeah. Don't, I feel like I kind of like to glorify those guys. Like, oh man, imagine what it must have been like sitting there and verifying like all those primes are just doing like all this work, all this mathematical work that they did, like locked up in their rooms. But like, I think a lot of those people were kind of like depressed and stuff. I don't know if that's totally true. I think a lot of them like loved it, but I mean, there's some characters that like personally said they like Wittgenstein, I think he was like pretty notoriously depressed. If you're just doing that all the time, it must get pretty sad. But I don't know, maybe you just love it so much. Probably different for different people. All right, next question, I guess. Oh wait, one thing, I never understood this. A while ago, I was looking at the Sieve of Eratosthenes, and there are like different sieves, and there's a faster one called the Sieve of Atkin, and I never, like, I wasn't able to fully implement this in programming, but I thought it was cool. It does some preliminary work and then marks off squares of primes, thus achieving better theoretical asymptotic complexity. Which is amazing. Like, someone made a sieve that much later down the line in 2003. And all remainders are modulo 60. Flipping an entry. And is this the best sieve, or is there a better sieve? Yeah, I think it does. Theoretical better time complexity. And I wonder if there's anything faster than this. Mark 2 and 3 is prime. I think there's some kind of like there's like memory trade-offs that you make though in terms of time complexity. Like you could you could just store every prime that we know of in memory and then just insta check them, and that would be like constant time. But I guess it would be however long it takes you to look it up. Linear time. I know that in analytic number theory people do lots with sieves, but this is really not my field. I think there are sieves for lots of things, yeah. Is there like sieve theory? Is sieve theory a field? Yeah, it's, I guess, linear time. The prime square free coloring operation can be described by the prime zeta function at 2 with constant offsets and factors. The real-based methods for deciding if something is prime using algebraic geometry and elliptical curves. Lenstra's algorithm. Sieve theory. Or the more general Gondra sieve. Sieve. Different types of sieving. It gets so complicated. All right, back to the homework. Only 2 more questions. Prove that n factorial is never a perfect square. N factorial is never a perfect square. Factorial also always makes me think of induction. We only check cases 3 and 4 because we solved this for primes up to 4. Well, less than the 4th prime of 11. Well, technically this doesn't work for 7, which is the 4th prime. It only works for the 5th prime. The 5th prime and beyond, so we have to check the 3rd and the 4th. Bertrand's postulate kills this. There's no primes, though. I mean, it's a product of primes. And this homework is all about primes, so... There's a prime between n over 2 and n. So the only multiple of p that appears in n factorial is just p. Only multiple of p that appears in n factorial is just p. Between n between n and 2n, a number being squared just means that every prime appears with an even exponent in the factorization. Right. That every with an even exponent Yeah, I don't understand where p is the prime guaranteed by Bertrand. Careful about the bounds. Since 2p is greater than n, it does not appear in n factorial. Wait, since 2p is greater than n, it doesn't appear in n factorial because all the factors are less. So 2p is the smallest multiple of p that is not p itself, so the largest power of p that divides n is p. Okay, I see that, I guess. That's pretty clever. What problem are we solving? 28, which part? Yeah, 28. Oh, Alexander's here too. Start by computing some small examples. Always a good idea. Oh, forgot I took my phone down. You know what, actually? I don't think this is the best way to do it. I think the best way to do it is with the programming language I have right here. Oh, I did start this with induction, which is not the way to do it. Check some small examples. Guess let's make the factorial function. Does type support recursion? And then let's return. Oh, we needed a body here. If n equals 1, return 1. Else return fact n times fact n minus 1. For I in range. Actually, it's probably just better to do range I dot map I fact I. That's cleaner. 4. I think we gotta join the content. What's the error? Unexpected argument? Why is that unexpected? That's literally expected. I think actually we don't need to. What do you mean unexpected argument? Is this type throwing it off? Unknown variable, fact. Okay, they in fact don't support recursion. I'm not doing this the non-recursive way. You wrote in types. Okay. To check some by Bertram's postulate, there's a p such that n over 2 is less than p is less than n. Since p is less than n, we know that p divides n factorial. But 2p is greater than n, so p squared cannot divide n factorial. We can pick p as long as n greater than or equal to 4. For small n, check manually. It doesn't really matter if n is odd. We only care about the size of the ceiling n over 2. But what if n is odd? You have to be a bit more careful. You need something like floor n over 2 or something to invoke Bertrand on though. When from n2 to 11, I see the idea. Key values are 6 and 10. Factorial is 6 is 120 times 6, 720. Through n from 2 to 11, and I see the idea. Key idea, look at the prime factorization. I guess I will do this on paper. So with 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. We got 2, 3, and 5. 10 factorial. 8. Or 2. What the fuck? What did I just do? 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Oh! Yeah. Yeah. I mean, so Pepe, what you're saying is cool and all, and you're a genius and all, but can't we say that there's gonna be there's these primes 5 4 3 2 1. Can't we say that their power is always going to be 1, and because the prime factorization is unique, there can't be. How do you say that more rigorously, though? Well, wait a minute. No, that doesn't work, because power is only always 1. That is exactly what Pepe is doing. Ignore that. That is not that's not correct in the slightest, because we have a bunch of other factors in there. He's showing that there always has to exist such a prime. Something very close to what you said is right, and another thing said equally close is very wrong. Yeah, so for some reason my fans are spinning up like crazy. OBS. Oh, I guess it's transmitting the camera. That takes a lot because it's like so high res. Okay. Bertram's postulate, there's a prime p such that n halves, or p is between n over 2 and n. Since p is less than n, we know that p divides n factorial, but 2p is greater than n, so p squared cannot divide n factorial. Okay, are you okay with this now? More or less. More or less. Using Bertrand's postulate. So as long as n greater than or equal to 4, for a small n checked manually, it doesn't really matter if n is odd. We only care about size. Issue is easily fixed. If n is prime, then we are done. Just choose p equals n. Otherwise, for odd n, if n is odd, wait, if n is odd, if n is odd, we know that n plus 1 is even, so choose between n plus 1 and n plus 1 halves for p. between n plus 1 and n plus 1 halves. By Bertrand's postulate, there is a prime p such that n halves less than p less than n. Okay. I followed this up until the second half, but I'll look at that as it comes to it. P less than n, p divides n factorial. Okay. But in the last problem, we already were forced to use it by a hint. We were also surprised. Is there a solution without Bertrand? I'd be interested if there is. But 2p less than n. So p squared, but 2p is greater than n. Two p is greater than n, then 2p can't divide n factorial. Why is this only for n greater than or equal to 4, though? Oh, because Bertram's postulate only holds up there. You can probably use Lagrange's formula. Yeah, you only need a new prime between p and p squared. The inside is the biggest prime power, and n factorial always has an exponent of 1. Oh, provided n greater than or equal to 4, because if it were less, then you could have p is less than 2. Well, if p equal to, then p squared cannot divide n. Is a prime p such that n halves we can pick p as long as n greater than or equal to 4. Doesn't really matter if n is odd, we only care about size. If n is prime, then we are done. Just choose p equals n, otherwise Okay, this issue is easily fixed. If n is prime, then we're done. Just choose p equals n. Otherwise, for odd n, we know n plus 1 is even, so choose n plus 1 and n plus 1 over 2. Just want to make sure I understand what's going on here, rather than just rote copying your answer. So by Bertram, or Bertrand, oh my god. Why are we worrying about parity of n? Yeah, I don't get that either. Why is my syntax highlighting messed up? There we go. Exists a p such that, and since p is less than n, p divides n factorial, but p squared does not divide n factorial. I guess also, like, I'm thinking more like just check the exponents of the sum can be even. Check the exponents if the sum can ever be even for all primes. Not really, you should just worry a little bit about it so it stays correct. A 2p is greater than n. 2p is greater than n, right? So p squared divides, it doesn't divide n factorial. For p greater than 1. Bertrand gives you a prime whose exponent is 1. Okay. So that's fine. That's good. As long as n greater than or equal to 4, why is that though? For small values of n. Because 2 less than the prime is... No, that still holds up. We can pick p as long as... we can pick p as long as n divides... or n is greater than or equal to 4. Well, if n is 3... I don't get why the restriction on n equals 4. N over 2 must be at least 2. Oh, n over 2 must be at least 2. Right. For this part. I see. Yeah, I got you. But what are the other issues here? What was Johnny saying that's the issue? Let me scroll up on that. Be a bit careful about the bounds, though. Since 2p is less than n, it does not appear in n. 2p is the smallest number of p. There's not really an issue. Uh, 2 over n might not be an integer if n is odd. Yeah, but if it's not an integer, like, doesn't the equality still hold up? I mean, isn't it just like pick like 2 over n plus 1 or whatever? Or the next biggest integer? It's more like if n is odd, then it does not make sense to invoke Bertrand on n over 2. That's why you should be careful. On n over 2. N plus 1 is even, so choose between n plus 1 and n plus 1 halves. Oh, yeah. But if p equals n, just choose. If n is prime, we're done. Just choose p equals n. Okay, because Bertrand is stated for integers, not half integers. Okay, I see. You can fix this. If n is an odd prime, then just p equals n. If n is odd and odd but not prime, then invoke Bertrand on n plus 1 halves. Yeah. Using types as Twitter. N is odd. But it's indeed easily fixed. It's just about writing down a correct coherent proof. There's a prime p such that n, yeah. Yeah. Yeah, okay. Yes, now I only need that Elon physique. Is Elon jacked? Block physique. Micro econ midterm tomorrow. Good luck. Good luck, Singu. Okay, yeah. I feel alright about that. He's the opposite of jacked. Oops, I just suspended. Yeah, that looks real. There's more fake than real stuff here. Yeah, he is built like a block. That's weird. Weird guy. What source would you recommend studying to vectors? You've got a great amount of knowledge. I don't have a great amount of knowledge at all. What happened to... What the fuck? My Vim buffer got messed up. There we go. Yeah, I don't have any good source of knowledge at all, but there are people in this chat that do. I'm assuming you're talking about linear algebra. You got a PhD position? Nice. For what subject? Dummit and Foot. Abstract algebra teaches you everything. Abstract algebra. Matrix groups, quaternion groups, group actions, cycles, cosets, Lagrange, Cartesian product and Zorn's lemma. Multi-agent planning, model-based reinforcement learning. That's awesome. Multi-agent planning. How do you feel about that? Like, are you talking about GPT models? Oh, I'm looking at exercise solutions, not a book. Okay. Yeah, I'm very excited. That's awesome. It seems like a very hyped field right now, for sure. No LLMs or GPTs. Awesome. That is very exciting. All right, this last problem. All right, before someone just drops the answer, I want to think about this for a sec. N factorial, n plus 1 factorial, n plus 2 factorial. Find the values for which of n, for which makes this a perfect square. So we want all the prime factors to be even, the prime exponents to be even. How is this gonna work? I gotta blow my nose. I'm gonna keep thinking about it. Yeah, it does look a little bit more interesting. Probably a Bertram's postulate problem again, just based on this whole homework involving Bertram's postulate. Yeah, what'll make this a perfect square? So we could use the same trick as before. And then p, we'd have a p that divides n factorial and it would divide all of those. Could we show the exponent is 2 in that instance somehow? Factor it, a miracle occurs. Okay. Good call. N factorial times, or plus n factorial times n plus 1 plus n plus 1 times n plus 2 for some reason my syntax highlighting just dies right there, which is fine. N factorial. Well, okay. We could factor an n factorial out of that. And then we get 1 plus that. Yeah, I feel like in general I should be doing more of this work myself. I think I'm relying on other people too much. But whatever, it's fun. Life isn't about... Well, it kind of is. Okay. So here... What? We're going to get n factorial times 1 plus 1 times that. So then that'll become n plus 2. I guess. Then we've got 1 times n plus 2 times n plus 1. So we could add 1 to this. And then get rid of that. And then this is n factorial times n plus 2 squared. Is that factor job right? Let's see. n factorial, yeah. 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 Okay. It's n factorial times n plus 2 squared. When is this a perfect square? Nothing's immediately jumping out at me. Try examples of n. Only going to give meta tips from now on. Okay, great. That's a good idea, actually. In fact, that's probably what we should be doing. This is about me getting better at math, just doing meta tips. All right. Try different examples of n. N greater than or equal to 1. So then we've got 1 times 3 squared. So that's 1 is going to be a valid answer for this. 2 times 4 squared is going to be 16. 32, not a perfect square. 3 is going to be also, why is this part B? Part A must be relevant. RIP, okay. When is A a perfect square? If A is a perfect square. When is an A a perfect square? If A is a perfect square. Part A is indeed relevant. Okay, well, n factorial is never a perfect square. N factorial is never a perfect square. You have to use the factorization of part A. What do you mean the factorization of part A? The factorization with something that's never a perfect square. Not of part A, but and part A. When and only when is it a perfect square? I mean, it's a perfect square when n factorial equals n plus 2 squared, I guess. And n factorial when n factorial equals n plus 2 squared. But that's a perfect square, and n factorial isn't a perfect square? So is this just never true? Exactly. AB squared equals a squared times b squared. AB squared equals a squared times b squared. If AB is a perfect square and A is a perfect square, what can you say about B? It's also a perfect square. Oh, because of Big Pepe's argument. Yeah. So when is this a perfect square? When n factorial is a perfect square. Which is, this is true when n factorial is a perfect square. But which from part A is only true when a which is only true my mind went blank when n greater than 1. So 1 so when you said not exactly but you were close, it's only true for 1. And Right, the property of AB is a perfect square. And A is a perfect square. Okay. I wonder in general, like, also n equals 0 works. So, Mr. IKEA. Okay. So, in general, like, I think I should be struggling more than I am. And so, like, meta hints are probably the best kind of hints. In terms of me actually getting good, which is the goal. Plus, like, if you have a master's degree or something, you're trying to teach students, this is good. If you're gonna be a PhD one day and broke like Johnny, then no. It's nobody's fault at all, other than mine. So this is done. Make it into a PDF. I have analysis class pretty soon. I don't really learn much from the lectures, though, so I wonder if it would be better to just skip it and try to learn the stuff on my own. That's risky, though. I think we're covering like the definitions of limits of functions right now. If you want to learn ML and RL. Do you have like problem sets for ML and RL? No, you probably don't. You probably just, yeah, attending the class. Yeah. I wrote something that types about mathematics. All right. People being sad doing mathematics. Are you really a great mathematician if you're not dead by a young age and have a shitty life? Galois dead by 21 in a duel. That's a banger way to die. Abel dead by 26. Ramanujan dead by 32. Tuberculosis. Once a generation. Gödel died by starvation after his wife died because he was too paranoid of poison to eat food made by others. Turing died at 42. Turing is a sad one, yeah. Forcefully drugged for being gay and father of computer science. Riemann died at 40, also of tuberculosis, father of complex analysis and complex geometry. Mariam Mirzakhani died at 40 by cancer. Female Fields Medal winner. Now it is clear that we should do to become better mathematicians is suffer. I mean, aren't there others that lived a long time, though? What about Euclid or Erdős? Yeah. Is living ridiculously dangerously? Yes, it is. Yeah. Yeah, you're right. I don't know. I do feel like I zone out way more than I should. Classes will dull your mind and destroy the potential for authentic creativity. John Nash. That's pretty harsh. Well, it depends on the class. Some I agree with. Yeah, Erdish did amphetamine. As people who climb or hang from cranes in construction sites. I have. Yeah, I don't know. I think my professors are all pretty solid. Right, I'm probably gonna be back later to uh, work on analysis. I know the Europeans will be asleep by that point, though. So yeah, all right, I gotta go to